Hello, hello. Oh, okay, I think I'm going to start. So I think I'm going to start. So, oh, okay, microphone. So I'm going to be talking about type refinement systems. And I wanted to begin, before talking about that, to talk a little bit about what is a type refinement system, so you know what I'm talking about. And so here's a plausible working definition of what I mean when I say type refinement system. So a type refinement system is just a type system which is built on top of a typed language as an extra layer of typing. So I put definition in quotes because, of course, this is not really a definition. So, you know, one issue is, well, okay, you know, what do I mean by type system? And, you know, it's a infamous problem that, well, type systems, we know that they're really useful in practice, but we don't really know what they are. I mean, it's hard to give a very precise mathematical definition of what a type system is that really includes all of the use cases that we use type systems for. And then, well, I said it's a type system which is built on top of a language which is already typed. So it's built on top of a typed language. Well, you know, what is a typed language? That's also something which is kind of, we don't really agree about that. So like I mentioned yesterday that, well, you know, we know that languages like ML, they're typed, we agree, but what about a language like Scheme? So Scheme is dynamically typed, so some people consider it to be a typed language. Also, pure lambda calculus is sometimes said to be uni-typed. So, okay, so type system is a bit fuzzy, typed language is also a bit fuzzy, but this basically gives the right definition. So, I mean, the right intuition for what a type refinement system is. Now, a bit of context. So when I talk about type refinement, the phrase itself, it comes from a research program that Frank Fenning started in the late 80s. And there's a bunch of his students which pursued this research program. He was also my former advisor. And so the phrase itself, I mean, when I talk about type refinement systems, I really kind of mean it in the sense that Frank and his collaborators sort of worked out. And when I talk about, so the course, the title is Principles of Type Refinement Systems. So what's the idea behind that? And one of the characteristics of this type refinement research program was, well, they looked at, they didn't look at a typed language in the sense of Scheme, which, it's legitimately, there is a legitimate sense in which Scheme is a typed language, but they looked at a language, in particular ML, which is, has a strong, it's strongly typed and it has a rich language of types, which also has strong theoretical guarantees. The types tell you a lot about your programs. There's also a lot of tools that come with it. There's Hindley-Milner inference, and there's compilers, working systems for ML. And the idea was that when you construct a type refinement system over ML in this project, it should be conservative in a very strong sense. So, not just in the abstract sense, but that you want the same nice theoretical guarantees of ML type system, and also the same nice tool support for these more refined types. Okay, so it was these kinds of strong constraints on building type refinement systems, which led to some principles which I think are important. I'm going to be talking about in this kind of type refinement research program. So a first very basic principle, which I hope to get you all to realize the importance of it. It's just the idea that there's a relationship of refinement, and it's useful to formalize that relationship. And that relationship is distinct from another concept which is a bit maybe more familiar, which is the concept of subtyping. So there's one concept of refinement and another concept of subtyping. And the basic intuition is when I write something like this, you read this as R refines A. These are two types, and this one refines this, R refines A. The intuition is that R is some property of A's. You know, A is some type of object, R is a property of that object. So for example, I can refine the natural numbers. Well, there are positive natural numbers, and there's even natural numbers, odd natural numbers. The property of being positive or being even or being odd are all different properties of natural numbers. And in the same spirit, the property of being red or tasty or being a banana are properties of fruit. So these are all types which refine the type of fruit. So there's one concept of refinement. Then there's another concept of subtyping. And in some sense, this concept comes after this concept. So I'm going to write that R1 is a subtype of R2 at some type A. So R1 is a subtype of R2 at A. We're here, it's implicit that R1 and R2 are both refinements of the same type A. Okay? So for example, we can write that odd is a subtype of positive at the type of natural numbers. The intuitive reading for subtyping judgment, again, this is an intuition, is that this subtyping judgment holds if for all A's, every object of type A, if A has the property R1, then it also has the property R2. So in this case, every natural number, if it's odd, then it's also positive. And sometimes we can write something like this. So odd is a subtype of pos. Here, I didn't index it by the type. It's implicit. Okay, it's fine. I'm leaving things implicit, being a bit relaxed. But if I try to write something like, say, even as a subtype of banana, it's a bit strange. So everything which is even is also a banana. So this is not really grammatical. This is not a well-formed subtyping judgment in this strong sense, because even refines the natural numbers, and banana refines the type of fruit. So we don't want to have this kind of judgment. So as something which is kind of related to this idea. So refinement and subtyping. An insight that emerged from, I think that it was valuable insight that emerged from this type refinement program is that it helps having this two-level view of typing, this hierarchical view. It helps to clarify this so-called distinction between types a la Church and types a la Curry. So this is something that you might have heard about, and I mean the so-called types a la Church or the intrinsic view of typing is that every term is uniquely associated with some type. It's an intrinsic property it's intrinsically associated with the term. The type is intrinsically associated with the term. And then on the other hand, in the Curry view, it's also called the extrinsic view, types are properties of terms. A term can have many different types, which are all the different properties that it satisfies. That's kind of the intuition or the philosophical view. It also has a practical aspect, which is that type checking is usually pretty trivial for types a la Church, the intrinsic view, whereas in the types a la Curry view, or the extrinsic view, type checking can be computationally expensive, or it can even be undecidable. So the basic intuition coming from type refinement is, well, a way of looking at this is actually that Curry refines Church. Okay, so that's like the slogan. But the idea behind it is that, well, when we talk about Curry-style typing, we shouldn't really talk about terms in a vacuum, terms in space. We're not, these Curry types are not properties of terms in space, but they're properties of terms which themselves have some intrinsic type a la Church. And this kind of maybe the reason why this principle emerged in this view of type refinement systems is because it's much easier to see when you're refining a language like ML, whereas when you're refining a language like the lambda calculus, it's hard to see what's the point of talking about this perspective. And it's kind of because really what's going on is that you have a recursive type that you're refining. So, okay, so what is the course going to be about? Kind of the structure is going to be in two parts. So the first part, I'm going to give you Okay, so the first part is going to be kind of organized around this slogan and kind of in taking it literal sense. So I'm going to give you a series of type refinement systems, which are idealized, and the type refinement systems constructed over the simply typed lambda calculus. So Church is simply typed lambda calculus, and I'll use that to introduce some important concepts, like talk more about this distinction between refinement and subtyping. I'll also talk about bidirectional typing and things like principal types. And then I'll also talk a bit about intersection types. And this part of the course is very much kind of drawing material and inspiration from this line of work. And it'll be very much in that style, in the style of traditional type theory, inductive definitions, proof theoretic style. Then the second part is actually going to be kind of there's going to be a kind of a split. So from a methodological point of view, I'm going to talk about a way of looking at type refinement systems from the perspective of category theory. And it's based on just a simple idea of looking at a type refinement system as an erasure functor from a category of typing derivations and refined types to a category of terms and less refined types. So this is going to be something that, I'll talk about how it has some nice connections to the theory of bifibrations that Patricia Johan talked about. And on the one hand, but it also that it gives us a way of talking about some other phenomena, which, connecting them to these principles of type refinement. So, for example, I'll talk about connections also to Hoare logic and separation logic, like Alex talked about, how to view it from the perspective of type refinement systems. And all of that part of the course is actually going to be based on work that I've done in joint collaboration with Paul-André Méliès. So it's going to be a bit of from the point of view of methodology, it's going to be different. I hope that you see that there's some continuity between the two halves in terms of the themes, and maybe if you don't like category theory, you can still enjoy the first part more. If you don't like inductive definitions, then maybe you'll have more fun in the second part. Then finally, just some general comments. Well, okay, there's a link I put here, which it has notes, lecture notes that I came up with, and I put them up this morning. If you find typos and bugs and things which aren't clear, please let me know. So I'm going to try to follow that more or less. I think I'm not quite sure about the time, how much material from there we'll be able to get to, but you can go there. Also, it has a lot more references. I'm not going to mention very many references, but you can find them there, and it includes some exercises. Okay. So I think we can go on. Okay, so okay, so I'm going to talk about refining simply type lambda calculus, and today's lecture I think is going to be a warm-up. And I'll describe a very basic type refinement system constructed over the simply type lambda calculus. So first, I just want to you've all seen simply type lambda calculus before, but I want to recall the definitions and give some formal definitions. So simple types. Okay, so the simple types are just the things which are constructed from atoms using arrows. So given a set P simple type hierarchy, okay, so types P is a set of types. It contains everything. So I'll write little p for elements of P. It contains everything in P. If P is in P, then P is in type P. And if A is in types P and B is in types P, then A arrow B is in types P. Okay. This is the simple type hierarchy. Now, terms. Simply typed terms. So I'm going to assume that we have variables and that every variable is associated with some particular type. So Church did something like this. He wrote the subscript. He wrote the type of a variable as a subscript. I'm not going to do that, but I'm just going to assume that every variable has a uniquely associated type. And then the definition of terms is going to be that if x is a variable of type A, then x is a term of type A. If T is a term of type A or B, and U is a term of type A, then U is a term of type B. And finally, abstractions, if X is a variable of type A, and T is a term of type B, then lambda xt is a term of type A or B. Okay. So this is all familiar. I just want to do this pedantically a bit. Oh, sorry. Yeah. Okay. Okay. So I just wanted to give this kind of pedantic definition, which you can't read, but to okay. So with this style of definition, we define the terms of a given type. Every term has a specific type. It's a term of type A. I'm going to write just typical notation. When I write something like this, it means that T is a term of type B with three variables, x1 through xn, and the x1 has type A1, xn has type AN. Okay, so now can everyone read if I write here? If I write large? So I'm going to take as a definition of the simply type lambda calculus, for the next 2 days, I think. I'm going to take it as just the simply, so lambda, when I write lambda arrow or the simply type lambda calculus, I'm going to mean the simply typed lambda calculus with a single atom, okay? So the hierarchy of types are just the types generated from a single atom, which is called iota. Okay, so this is a simply typed lambda calculus. Some examples. Lambda xx is a term of type iota arrow iota. There's a little bit of subtlety here, so you might think I should be writing, or how is it? So, right. So Church would write something like this, where iota is a index on x, so we know that it's a variable of type iota. I'm going to leave that implicit, but I hope that it's clear. Just some more examples. Lambda x, lambda y x. is a term in this language of type Yoda, error, Yoda, error, Yoda, and so on. So everything is, it's a simply type lambda calculus. Everything is very simple because we just have a single atom. Now the idea is we're going to start with this language. We're not going to change the language. It's just simply type lambda terms with the generated over a single atomic type. And now we're going to build type refinement systems which let us specify more precise properties of terms in this language. Okay, so I'll move here now. Okay, so now we're going to talk about refinement again, subtyping, and typing in. Now, a little idea, which I'm going to call this lambda arrow with subtyping. So the idea here the idea for this type refinement system is, I said, okay, we have a single atomic type Yoda. This is, Church used Yoda and he also used Omicron. I think he took this from Russell maybe, and these were kind of logicians and philosophers. So Yoda is an abstract type of individuals. Now the idea of this type refinement system is we're going to replace this unique atomic type with a collection of atoms. And we're going to see them as representing different properties of individuals. Okay, so I'll give you an example. I think I'll include it. I'll put it here. So we're going to replace the singleton set, a singleton atom, with now another larger collection of atoms. And I'll give you an example. So for example, we could take this set, different possible properties of individuals. Okay. This is our new set of atoms. And well, these are supposed to represent different properties of individuals that it might have. And there's some implications between these properties, right? So every dolphin is a mammal, and a carrot is a vegetable. So we're going to add, assume we have a preorder so a reflexive transitive relation on the set of atoms. And I'll give you an example. So in this case, we have, I think I worked it out. I'm drawing a Haas diagram. So there's the implications going up along the lines. Every llama is a mammal. A dolphin is a mammal. It's also a marine animal. A jellyfish is a marine animal. Mammals and marine animals are animals. Carrots are vegetables. Okay. So this is an example. And we're going to assume we have something like this. So we have a set P of atoms, and we have a preorder on P. And now I'm going to define this type system with respect to that. So I'm going to begin by defining, before defining the typing relation, I'm going to define these two relationships of refinement and then of subtyping. So first I'm going to define refinement. So definition, refinement. Let me try to write larger. So the refinement relationship I'm going to write it like this again. R refines A, where now R is going to be something in types of P. It's going to be a simple type again, but now a simple type generated over this collection of atoms, or some arbitrary collection of atoms. And then A is going to be in types of, well, just this boring simple type hierarchy with one atom. So I'm going to define the refinement relation and just inductively like so. So any atom P, which is a member of this collection of atoms, refines iota. So again, mammal refines iota, llama refines iota, and then okay, so we're going to say that an arrow type, RROS, refines an arrow type A arrow B. Well, okay, what do you guess this should say? So we're going to say when R refines A and when S refines B. If R refines A and S refines B, then the arrow type ROS refines the arrow type A arrow B. Okay. Now we've defined refinement, and I'm going to define subtyping. So we have a subtyping relation. And it's going to look again like what I wrote there. So it's going to be a relationship. It's going to be a relationship between R1 and R2, where R1 and R2 both refine A, right? So what that means, R1 and R2 are going to be, if we spell it out, these are both members of types of P, and then A is a member of types of iota, and they both satisfy this relationship. So we're going to define it inductively again. And well, so again, there's going to be a case for atoms, and there's going to be a case for function types. So we define P1 is a subtype of P2 at iota. These are atoms. Well, just if P1 is less than or equal to P2 in this partial order that we've taken as an assumption. And then R1 S1 is a subtype of R2 S2, and now again this is at a type A arrow B. If R2 is a subtype of A, R2 is a subtype of R1 at A, and S1 is a subtype of S2 at B. So, you might be familiar with this rule. So the subtyping rule for function types, where it's covariant in the range and contravariant in the domain. I've been very pedantic about including the indices here on the types. But to make clear that again the subtyping relationship is between two different refinements of the same type. And these two relationships for now, yes?
I wanted to ask, for both the refinement and subtyping, does that hold for a partial refinement of an error type?
A partial refinement of an error type?
So say that you have R is a refinement of A, would it then hold R to B is a refinement of A to B? Does that still hold?
Say again that it.
So on the refinement side,
Yeah.
or other side,
Yeah.
you take off the second trying to get either S refined B or S1 subtract S2.
Yeah.
Take that off, can you still say that R1 to S, just S is refinement of R2 to S?
I mean, I think it will become more clear later on. So, yeah, so I mean, I want to just introduce this for now, and it's kind of abstract for now. And I began by saying that there's this distinction between refinement and subtyping, which is important. I didn't say why, and it's kind of for now it's very abstract, but I'm gonna. I hope that it will become more clear as it goes on. And yes.
Yes, maybe a different way to ask the question is: can we say that the refinement relation is reflexive, or does it just relate to things different?
So this is that's a good question. So this is exactly what I wanted to just mention now, to give you some formal properties that highlight the distinction between these. So two observations. So the first is that the refinement relationship is actually a functional relation. So that means that
Are the indices mentioned that if R2 is a subtype of R1, then R1 to S1 is inverse with that?
with the R2 subtype of R1 instead of R1 subtype of R2, yes. So I mean, that's the intuition that this is saying something about functions from A to B, that if they satisfy this property, that they take R1s to S1s, then they also satisfy this property, that they satisfy R2 S2s, and this turns out to be the right rule. But so I want to make just two simple observations that the refinement relationship is a functional relation. So for every R in types P, there exists a unique A in types iota, such that R refines A. Okay? And then, on the other hand, the subtyping relationship is a preorder. So it's reflexive and transitive. So we have that R is a subtype of R at A for all R refining A, and that R1 if R is a subtype of S at A, and S is a subtype of T at A, then R is a subtype of T at A. Okay. So this is just a formal property of these two different relations, which shows a bit about why they're different. Maybe one of the reasons why it's sometimes it's hard to distinguish these, they both kind of look like subset relationship. If we think about types as sets and we want to talk about subtyping as inclusion of subsets, okay, that's fine. But then when you look at refinement, well, the relationship is functional. That's something which that's strange to talk about this relationship as being functional. And I'm gonna get back to that a little bit later. But now, let's give some examples. So, okay, just some simple examples. If we take this type, we can refine it in different ways. This refines A and okay. And these are all different refinements of A. Okay, but then if you look at the subtyping relationships which hold between them, so R is a subtype of T. Why is that? If you have something which will take a given any transformation from mammals to mammals will return a mammal, well, you can use that as given a transformation from animals to dolphins, you can get an animal. And then S is also a subtype of T, and those are the only relationships which hold. Okay. How am I doing with time? Let's go here. Okay, so I've defined refinement, I've defined subtyping. Yes? So I'll mention typing, and that's gonna come up in the idea of the subsumption rule. So I'm gonna define typing for this, this type system, which I'm calling, and there's going to be a typing relation. It's going to look like this. So T is a term. It's a term of type A with some context of free variables gamma, with some types which are mentioned in gamma. Then R is going to be some refinement of A, and then pi is going to be a refinement of gamma. And I guess I didn't define what it means for a context to refine another context, but this is just what. So suppose that pi is some list of types for the variables, it's going to refine gamma if every Ri refines Ai. So the typing relation is again going to be defined inductively. I'm going to give you 4 rules. Okay, so in a context pi, X has type R if X R is an assumption. Then these rules are going to look very familiar, most of them. There's variables, there's application, there's lambda. Okay, these are standard, and then now there's another rule, which is really the one which makes it interesting, is the rule of subsumption. And that says that we can give a term T a type S if we can give it a type R, and R is a subtype of S. This is called the subsumption rule. And now this is the rule which kind of expresses the idea that R is a more precise type. If we can give T is a type R, and R is more precise than S, then well, it also has the type S. Now, okay, these are the rules. In all of this, I didn't mention it explicitly, but it's implicit. There's various constraints are implicit. So, when I write this, we know that R arrow S, it refines some A arrow B. Pi refines some gamma. Lambda xt, it's a simply typed term which has the underlying type arrow B. And then the same holds here. We know that the T has, we know that these are kind of implicit conditions in the rules. I'll erase them now. Okay. So now I'll give you another example. Okay, so another example. We take the sequential composition combinator, which is just lambda f, lambda g, lambda x, g applied to f applied to x, which is of type I arrow I, arrow I arrow I, arrow I arrow I. And it has this is its underlying type is this thing, but we can also give it more refined types. So for example, we can show in this type system that sequential composition has this type. Okay, and you can think about that intuitively. why this works out. And so we can show this. But then this, we can't, for example, we can't show this. So okay, so I'll let you think about why this works out if you want to. This, we can't give it this. We can't give sequential composition this more precise type because, well, if we assume that the F takes llamas to llamas, that the G takes vegetables to vegetables, we can't compose them. We can't get this type. Okay. So let me. I think I should try to go a little bit more quickly. So there's a few exercises in the notes which I think are fun, which to try to get a little bit better intuition for what you can and can't do in this type system. I want to talk about something which is an important idea, and we can already see it even in this very simple system. And it's the idea of there's the connection between subtyping and eta expansion. Okay. Yes? This one? So it's saying, I mean, so you cannot give sequential composition this type in the type system with those rules. I mean, you can try to give it this type. You'll see that it's not possible. And I mean, you can think about the intuition for why that's not the case, and the example is in the notes. But so, okay, there's a little observation about this type refinement system, is that there's a connection between subtyping and eta expansion, and there's a sense in which you can see instances of subtyping as hiding implicitly eta expansion. The idea here is, well, suppose that we take the subsumption rule and we restrict it in like this. So I'll call this subatomic. So it's just the subsumption rule, but just restricted to atomic type. So basically, we get rid of we're just considering subsumption at atomic type and not at functional type. There's a sense in which this is actually enough. And the observation is, well, okay, so proposition, if you have, in this type system with the subsumption rule replaced by the atomic subsumption rule, the following rule is admissible. And it says that, well, you actually, okay, so it's almost this. Where? Okay, I've just copied the subsumption rule, but it's not actually this. It's actually the eta expansion of T at the type A. And what is this? It is actually the iterated eta expansion of T at a type A. And let me just define that for you. So It's defined by induction on the underlying simple types. Okay? So eta, the eta expansion at an atomic type iota of T is just T, and the eta expansion at a type A or B is lambda x, and we're going to eta expand x, but now we're going to eta expand it at the type A. We're going to apply T to that, and then we're going to eta expand the result at the type B. So this gives an inductive definition of eta expansion, the iterated eta expansion at a type A. So then the observation is that if a term T has a type R, and now R is a subtype of S at the type A, then we can eta expand T sufficiently, and we can give it the type S, where we never have to apply this rule. We just have to apply this atomic subsumption rule. So you can do as an exercise, you can try to prove this, and the proof is pretty simple. And one consequence of it is that, well, if you have that consequence, if R is a subtype of, if R is a subtype of S at A, then if R is a subtype of S at A, then we can show that we can type the eta expansion of X at the type A, and show that assuming X has type R, then the eta expansion has type S, again in this system just with the atomic subsumption rule. So this is again a sense in which you can reduce typing, you can reduce subtyping to typing of the eta expansion. This is one direction, and actually the converse is actually also true. So the converse says, yeah, I mean, if this holds and this holds, and so there's an equivalence between subtyping and typing of eta expansion. Yes?
So in the context of the country type and calculus and only gave the type of a parameter, when you define the eta expansion, are you saying when you eta expand a term, you have the freedom to decide to annotate the parameter of that however you want?
I think this is the issue. I said that I was kind of leaving implicit. I'm not going to write explicitly the types on the variables, the underlying simple types involving the iotas. But because I was saying that I'm going to say that it's implicit from, we have a way of getting the information about each variable has a specific simple type. Then we might assign it more refined types. But I mean, does that make sense?
It seems that the choice, like what we're leaving implicit there,
Yeah.
is actually like the singular important thing in making this proposition true, right?
Here?
Like the reason that you can eta expand a function
Yeah.
and type it with a more specific type is that strictly speaking, you're able to like annotate the parameter of the new function with a more specific type.
We need to have the A in order for this to make sense. I mean, we need to know the type A somehow. So you could put the annotations explicitly on the variables. For example, you could annotate the variables by the types. Okay, so this is I've defined inductively a typing relation, a subtyping relation, refinement relation. But I haven't said anything about how to actually check whether a term has a type. And so how do we decide, can we decide whether a term has a type? And you might hope that the answer is yes, because this is such a simple type system. But, well, okay, so first, what about subtyping relation? The way that we've defined it here, the typing relation referred to the subtyping relation. So first, what about the subtyping relation? Well, did I erase the definition? Yeah. So again, if you look at the definition of subtyping, it's pretty easy to see that it's decidable, and there's a very simple procedure for deciding it. We can just read the rules bottom up. So for function types, to decide whether R1 or S1 is a subtype of R2 or S2, we just go up to the premise of this rule and we check, well, is R2 a subtype of R1, S1 a subtype of S2? And then at atoms, well, we're going to have to assume that this atomic relationship is decidable. Okay, we assume it's decidable. Then it's clear subtyping is decidable because it has this bottom-up interpretation. Well, we can't, that doesn't work for the typing relation. And so, one example of this is, well, something which you can always do. I mean, this is just an indication of why there's some difficulties here. We might try to type T, to show that T has type R. Well, we can use the subsumption rule and maybe we'll use it with reflexivity. And well, we've reduced the problem to checking that T has type R. So we haven't made progress. Okay, this is maybe that's a bit. Okay, why would we do this? But more generally, the problem is if you look at these two rules, the subsumption rule and the application rule, the problem is they don't have a bottom-up interpretation. So suppose that we're here in application. We want to check that a T applied to U has type S. The problem is that we need to come up with this R, and we don't really have any guidance for coming up with R. And the same thing here, the subsumption rule. Well, we're going to show that T has type S by showing that it has type R and that R is a subtype of S. But where do we get the R from? A concrete example of this is so sorry. So just an example, this is a more complicated term. suppose that we start with our items now. We have just two refinements of iota, which are bottom and top. Bottom is a subtype of top. We can show this. But to show this, it turns out that you need to show that this term has type bottom arrow, top arrow, bottom arrow, top arrow, bottom arrow, top. And where do we come up with this thing from? Somehow we had to guess that this was the right type, that, well, this term, lambda z, lambda w, z has this type. And so then this, we can check that this term has this type, and then we apply it, and so we get that type. But we had to come up, when we were asking about this, we didn't have the information about this type. So where did we come up with that? Okay, so this is the issue. And there's different possible responses to the issue. One possible response that you might think of is, well, what about some type of type inference? So if you're familiar with programming in languages like ML, you're familiar with the idea of type inference. We don't always have to write annotations. The system can infer types. And in order to do that, something that it usually needs is a principal type. Let me just a question. Zena, so how much time do I have left? 10 past 12. Okay. I'm trying to think if I want to try to get through everything. So, okay, let me first just define what a principal type, what it means for a term to have a principal type here. So, define suppose that you have a term T. It has some underlying type A and a context gamma. Okay. And now suppose that you have a refinement of the context. So you specify types for the variables. Then a principal type for T in context pi is going to be some refinement R of A such that, well, T has the type R in the context pi, and for any other S refining A, if T has the type S, then R is a subtype of S at A. Okay? So that's the sense in a pi principal type is a type which is the most precise type that we can give to T in the context pi. So that's a reasonable definition of principal types. The problem is that, well, you don't have principal types in this sense in this language. And it's actually, it's for stupid reasons, but so, okay, suppose we have the identity term at the type iota arrow iota. Well, does it have a principal type? I have to tell you first, okay, we have to fix some set of atoms. So you can take it to be the one that I originally drew, but I erased. But does lambda XX have a principal type in that, does it have a principal type with that collection of atoms? We'll know, because we can give it the type, for example, animal, arrow, animal, and we can also give it the type vegetable, arrow, vegetable, and neither of these is a subtype of the other. So what do we do? Okay, that's the question. What do we do? And there's two possible responses. I'm sure there's more than two, but okay, there's at least two possible responses. And the first response is to say, well, actually, talking about principal types in this setting is not really what, it's kind of a red herring. Really, we should be talking about so-called principal type schemes. So what does that mean? Well, for example, the identity term we could give it an abstract type. Well, we say, suppose that we're going to abstract away now from the collection of atoms. And we're going to say that, okay, suppose you have some collection of atoms. Well, you can give lambda XX the type P arrow Q, where, so long as P is less than or equal to Q in the ordering relation. Okay, and another example. The example I gave before of this term, you can give it this abstract type where you assume that some constraints hold. So, okay, the idea here is that given a term, an arbitrary term, we can try to cook up a set of atoms and the relationship between the atoms, which captures all the possible types for the term. I think I'm not gonna describe it more formally than that. You can look in the notes some more formal definitions of what exactly it means a principal type scheme, and some exercises related to that. You can try to write an algorithm, write a program that will compute these. But this is one possible approach, and it's related to the kind of inference you see in Hindley-Milner-based systems like ML Haskell, that you're computing a set of constraints. And then type checking is just in the end, well, we check in our particular case, does it satisfy the constraints? But now there's another possible response, which is called bidirectional typing. And for various reasons, this turns out to be a more, this approach has advantages, which in this simple system, it's not so obvious why this other approach is better. But it turns out that as we scale to more sophisticated type refinement systems, this kind of approach becomes difficult, and I'll get to that in the next lecture. But so I'm going to try to tell you now about bidirectional typing. So the basic idea is, well, we saw that in this language, not every term has a principal type. And we got very worried about that, and we said, oh, no, we should be computing principal type schemes. There's another response, which is to say, well, actually, OK, not every term has a principal type, but maybe some terms have principal types. And that's enough. And it turns out that it is in some sense. And it has this bidirectional typing turns out to have nice connections to properties of lambda calculus, theoretical properties of lambda calculus. And so I'm going to I want to recall for you the definition of so-called neutral and normal terms in lambda calculus. So this is just a classification that shows up, and I'm going to define properties of being neutral and normal. So a variable, variables are neutral. Maybe this is too small. If t is neutral and u is normal, then t applied to u is neutral. If t is neutral, then t is normal. And if x is a variable and t is normal, then lambda xt is normal. Okay, that's a long definition in words. To make it just more concise, you can describe it as a little grammar of neutral terms together with normal terms using E and M, and neutrals are variables, or the application of a neutral to a normal. Normals are either neutrals or a lambda abstraction of a normal. Okay, so that's this classical definition of neutral and normal terms, and the motivation for the definition, or one observation is that, well, if M is normal, then it's beta normal. It has no beta radices. You can just look at the definition and you'll see that it enforces syntactically that there's no beta radices. But now the observation, which is cool, is that there's a simple procedure for looking at a normal term and checking whether it has a type, where we use the fact that we can infer principal types for all of the neutral subterms. So we can get all of the neutral subterms, we can give them a principal type, and we can use that to check whether the normal term, whether the term has a given type. And that leads to the idea of bidirectional typing. And what's nice about it is also that it's very easy to define. So I'll define it for you here. All that we do is we split the typing relation into two relations. So we have a judgment which is called the synthesizing judgment. For a neutral term E in a given context pi, I'm going to synthesize a type R. And for a normal term in a given context pi, for a given type S, we're going to check whether M has the type S in the context pi. And, well, actually, so the rules, what are the rules? Well, you can just refine these rules. So the variable is going to be, variables are neutral, right? So X is going to synthesize a type R if X, if the type X, R is the type for X in the context, then we can synthesize the type R. So this is the synthesizing version of the variable rule. Application, we're going to assume now that this is a neutral, so application is the application of a neutral term to a normal term. It's going to synthesize some type Let me write the rule and then read it again. So if E synthesizes a type R or S, and if M checks against the type R, then in the same context, E applied to M synthesizes the type S. So intuitively, the reason why what's cool now is that we're actually reading the rule going from top to bottom rather than bottom to top, because it's synthesizing a type. Let's continue. So the lambda rule is checking. We check the lambda xm against the type ROS. Well, we check the body. We add the type R to the context because it's given. And then finally, subsumption. So this is also where something interesting goes on. Well, so we said that normals, the grammar I gave here, are either lambdas or neutrals. Suppose that the normal is actually a neutral term. In this case, well, we can synthesize a type. We want to check that E has a type S. We synthesize a type R for E. And then we check that R is a subtype of S. Okay. So this is bidirectional typing. And what's neat about it is it looks almost exactly the same as the typing relation. But the idea is that now it's algorithmic. So in the terminology of logic programming, these relations are well moded. So this pi is an input, the term E is an input, and then R is an output. And then these are all inputs. And we can read this as an algorithm. One of the exercises I'm going to give you is to implement this for this type system. Now, you can see in the notes some theorems that show that this actually works, that it's complete in a sense. This is complete for normal and neutral terms. But okay, you might be wondering now, this seems to work really great for normal terms, for terms with no beta redices. But what about terms with beta redices? We might want to write some programs which actually run. So that's not a problem. The basic idea is that we're going to, wherever we have a beta redex, that's precisely where we're going to put a type annotation. So I'm going to copy this grammar. Again. So now the idea is we're going to add a coercion, a sort of virtual coercion from normal back into neutral. And that's going to come with a type annotation. So we add this, and then you can see that we can represent any term with beta redices. We can fit it into this grammar, but wherever we have a beta redex, we have to put a type annotation. And now we add one rule, which is the annotation rule. And it says that well, an annotated term, M with the type R, will synthesize the type R, so long as it actually has the type R. We check that it has the type R, then it will synthesize the type R. And that's it, that's bidirectional typing. Now, in terms of time, should I? Do we have 5-10 minutes? Okay. So there's some more exercises in the notes and explaining some more properties of this. And I recommend that you try to implement the algorithm. I want to just explain to end this today a nice way of visualizing bidirectional typing. That's why I needed the colors. Okay. So there is a way of visualizing lambda terms as graphs. This is an old idea. I'll give you some examples. So we have a lambda term. I'm going to represent it as a graph. Not enough space. Let me draw it first and then. Here's a more complicated example. Okay, so this is the representation of lambda x, lambda y, x applied to lambda z, y, z. This is the representation of the term that I wrote earlier, but I think I might have erased. And you can, like the basic idea is that you have two kinds of vertices, lambdas and applications. And to make it clear the correspondence, you can annotate the wires by subterms. So this is the lambda x, and there's the variable x which goes out on this wire. And then there's incoming is the body, which is so the lambda y x, lambda z, y, z. This is the lambda y. So here we have y going out on the wire, and the body is this expression x lambda z, y, z, and I can keep going. So here we have x, and we have an application. It's the application of x to this lambda z, y, z, y. Sorry, that's z. And this is y applied to z, so we get y applied to z here. And similarly, okay, this is an application. Here we're going to have the lambda z, lambda w z, lambda f, lambda y, lambda x f applied to y x, and so on. Y. Sorry, this is x. I screwed up. Okay. The basic idea of this representation is that you look at the application nodes and they take incoming argument t. They take a function and an argument and then they spit out the application. And you have the lambda nodes, they spit out a variable, they take a body and then they spit out the result. Okay, so you have these graphs. And well, now you can refine these diagrams by keeping track of the normal neutral distinction. So you can see the normal neutral as a coloring protocol on these diagrams. And let me show you there. So I'm going to draw a neutral in blue. And a normal in red. Application takes a neutral, applies it to a normal and returns a neutral. Lambdas, they spit a variable which is neutral, they take a body which is normal and they return a normal. Now we need, in order to build terms, we need the coercion from neutral to normal. So we're going to add a little I should try this. A little box, which is a converter box from neutrals to normals. And we're also going to add a little coercion in the other direction, which is going to let us go from normal to neutral. But now the idea is, well, we can put types on these. Okay? So here, the term t, let me back up. So I'm trying to think how much time I have. Okay, I'm going to assign types to these, to the wires now. I'm going to annotate the wires with types. So here the function is supposed to have type ROS. The argument is supposed to have type U. It's supposed to have type R. The result is going to have type S. Lambda abstraction, the variable has type R. The term has type S, and then the lambda abstraction has type ROS. So the cute thing is that actually, if you draw your lambda terms like this, and you color them in, and then you just reverse. You look at the blue wires. No, so the blue ones or the red ones? No, you look at the red wires, and you reverse the direction. I'm going to take all of the red wires and reverse the direction. So here, these rules, they actually correspond. So this, these diagrams, they correspond to the application and lambda rules. So application says we're given the term T, which has synthesized the type R arrow S. Now we're going to take R, and we're going to use that to check the U. And then we can synthesize the type S for the result. The lambda rule says we're going to check the lambda against the type ROS. Well, then we can use that. We're going to spit out the R here, which means that we're going to synthesize the type R for X. And now we're going to check the term T, the body, against the type S. But now, well, what about the coercions? Here you have two inputs. So you have a type S, which is here, and you have a type R, which is here. And they both come into this coercion from the neutral to normal. And well, all you have to do is you have to check that R is a subtype of S. This corresponds to the subsumption rule, which is the coercion from neutral to normal. And then now this is the last. This corresponds to the annotation rule. And now we've reversed the red. When we reverse the red arrow rule, we see we have two outgoing wires. And so, well, here, this is where we put the annotation explicitly on the term. It's an annotated term R. Well, now we're going to check that M actually has the type R. And if so, well, then we can synthesize the type R. So in the notes, you can see it's worked out with this example. And I think I'll end there. We can go to lunch. Okay. Are there questions?